And for a square lattice, it's square. For a triangular lattice, it's a hexagon, and so on and so forth. Okay? Now, Wilson says, let's forget about the fact that it was a square lattice or some other kind of lattice, because really, when you go to very long length scales, the lattice has vanished. Everything is slowly varying. Lattice itself is gone. So he's going to replace it by a d-dimensional sphere. The radius of the sphere is what we will call the cutoff. Okay, this is a sphere in momentum space. Okay? That cutoff, when you begin your renormalization group procedure, is going to be of order 2 pi over the lattice spacing. Okay, because that is typically the size of the rho 1 zone in some lattice. Okay? The point of Wilson is it doesn't matter exactly what the shape was, even exactly what the size of it was. Doesn't matter. Because what's going to happen is that we're going to shrink it. We're going to integrate out little narrow shells like this. Okay, and every time we integrate it out, we will get some contributions, some extra contributions from the parts that we've integrated out. Okay, into the effective theory, and these coefficients that are sitting here will flow. Okay, that's the whole idea. Then remember, we had basically grad phi squared over 2 plus m squared phi squared over 2 plus lambda phi to the 4th over 4, and then I put a dot dot dot. Okay, so what are all these dots? Well, in particular, I could think of something like this, plus u8 phi to the 8th, and so on, right? Maybe I could also think about, the Laplacian of phi whole square, and so on. Remember, every term I write down has to have the symmetry of the eigenvalue. Okay, it has to be even in the field. Okay, the field is phi. That's why I'm not writing down things like phi to the 7th or phi to the 3rd. If I write that down, that will be a very different theory. It will not be the eigenvalue. It will be something else. Okay? So I can have all these terms, and then the question is, what about these terms here? Can they ever be important? And Wilson will give us a procedure for telling whether some interaction is important or not. Okay? And we know what that is, whether it's a relevant interaction or an irrelevant interaction at some fixed point. Okay? So based on that, you'll be able to rigorously throw all these things away. Okay? And then we look at the flow of this guy and that guy, and then we ask whether there's a fixed point. Yeah?
It might happen that you have symmetry only at your low energy scale. Only at that scale you have that symmetry.
Well, remember, we start from what we now regard as a high energy theory. So in condensed matter physics, we usually know what the starting Hamiltonian is, and then we want to know what the critical behavior is. So we are integrating out the high energy degrees of freedom. So we actually know what the Hamiltonian is, what the symmetries are. Okay? It's exactly the opposite of particle physics, where you observe some phenomena, and from that you try to infer what the theory is. We know what the theory is. We are trying to infer the phenomena. Okay? Right? It could happen that somehow the low energy theory at the critical point can have extra symmetries than the symmetries that you have here. That can happen. Okay? All right? Okay. So that's the grand scheme. So let's see how far we get. So now let's make this a little bit more precise. Okay, so we're going to write down this theory, and we're going to write a cutoff here. Okay, and again, I'm going to write 1/2 grad phi squared plus 1/2 n squared phi squared plus lambda over 4 phi to the 4th plus dot 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 d to the dx. What do I mean by this cutoff on a real space integral? What I mean is that my field phi has momentum components only up to that cutoff. that is what I mean. So the momenta of these fields are restricted to this ball, this d-dimensional ball. Okay? Good. Now, this d-dimensional ball, I will introduce this little narrow region here, and I'm going to integrate it out. I'm going to ask what happens. Okay?
Why are you writing lambda there in the special?
Here? This is what it means.
Oh, okay.
It means that my fields don't have momentum components higher than lambda. That's what it means. Okay? Good. Now, let me define my field to be a sum of two fields. Okay? This guy lives now within this shrunken ball. Okay? And this guy lives in that very narrow shell, the spherical shell. So let me write that. So let me define the following. So d lambda by lambda will appear a lot. I will call it dl. Okay? So let me write it the following way. This phi less of x, you should think of them as the slow fields. And phi bigger, you should think of as the fast fields. Okay? So the slow fields are basically integrated up to lambda times 1 minus dl. And these other guys, the fast fields, of course, will be integrated from lambda times 1 minus dl up to lambda, right? Same thing. All right? Now, the nice thing about this is that if I look at the quadratic part of my action, they're completely separates between the fast fields and the slow fields. It's only the non-quadratic part that will couple them. So, let me write it in the following way. The total action will look like an action for the slow part, an action for the fast part, and some interaction part between the two of them. Okay? What will it be? Well, the slow part is basically going to be the same thing. I can write it either in momentum space or in real space. Okay? Let me write it first in momentum space and then I'll write it in real space. So it will be, right? There's that, e to the dk. I'm getting tired of writing 2 pi to the d, so I'll stop writing it. Okay? You will just imagine that it's there. Okay? Then there's this phi tilde of k, phi tilde of minus k squared plus m squared over 2. You remember this from yesterday? Right? This was the quadratic part. Okay? And then there's some horrible mess here. Okay, so let me write down what this horrible mess is. So basically there will be 4k integrals. So d to the 4 k1, d to the dk1 up to d to the dk4, but each of them will go only up to that. Right? And then there will be a phi tilde of k1, phi tilde of k2, phi tilde of k3, phi tilde of k4. And then there will be some delta function. Right? Because all the k integrals have the same x. And you do that x integral, you get a delta function. Of course, this delta function is not really a delta function. Because to get a real delta function, you have to integrate over all momenta, right? You're not integrating over all momenta. Schematic. Okay? Fine? Alright. In other words, I can just rewrite this in real space as d to the dx 1/2 gradient of phi less squared plus m squared over 2 phi less squared plus lambda over 4 phi less to the 4th power. Okay? Alright. Now what about s bigger? Well, here it is. So it goes from 1 minus dl to lambda times 1 minus d to lambda. Okay, some d to the dk. Again, 1/2 k squared plus m squared. This k squared now, I might as well call it lambda squared. Right? Because it's in a very narrow shell. And all the k's in that shell are nearly lambda. Okay, so there's that. And then there's this phi tilde of k and phi tilde of minus k. And then there's this phi fourth term, which is something similar, except now the integrals here go between lambda times 1 minus d to lambda. Right? Alright, what about the interaction term? So that's where all the interesting stuff is. So let me write it, and then we'll go back to do some necessary things with just the less, the s less, because we have to do some more rescalings. Okay? So let's first write down what this S interaction is. So S interaction is best written in real space. So it looks like this. So it's a lambda over 4 d to the dx. Right? So remember, the basic idea is you have your phi, which is a sum of phi less and phi bigger. So you've already taken the phi less to the fourth part over here, right? So there's some parts that makes up phi less and phi bigger, right? What will they be? Well, there will be a phi less cube times phi bigger. There will be 4 of those guys. Correct? Because if you have phi less plus phi bigger, sorry, 3 times. So in other words, I'm expanding the fourth square. Okay, phi less plus phi bigger to the 4th power. I just expanded out, right? So there's this, then there's 6 times phi less squared, phi bigger squared, plus 4 times phi less, phi bigger cubed. Okay, that'll be the interactions. Okay, and this is where all the flow will really come from. Okay, the most interesting parts of the flow. Okay? But first, let's do the simplest possible.